Hello and welcome to our lesson on simplifying rational expressions. So in this unit, not only will we look at rational expressions, we will transition to solving rational equations, and then in the next unit or the next module, we'll be looking at rational functions. Now, what does it mean for an expression or an equation or a function to be rational? Well, if you remember anything about your beginning algebra class, you probably started off by classifying numbers. And when we classify numbers, we start off with every number is a real number. And then the real numbers break into two subgroups, where some of the real numbers are what we call rational numbers, and then some of the numbers are what we call irrational numbers. Hopefully this is sounding familiar. This isn't really the point of the lesson. I just want to make sure you're clear on the word rational. Okay? So how do we differentiate between real numbers that are rational and real numbers that are irrational? If I gave you an example of a number, do you think you could identify what category it belongs to? Like, let's say the number 4, for instance. Do you think 4 is a rational number or an irrational number? Well, in fact, 4 is rational. So let's stick that over here. How about the number negative 4? Let's go to pen. Do you think negative 4 is rational or irrational? Well, in fact, negative 4 is still rational. I'm going to put that over here. How about 0? Do you think 0 is rational or irrational? 0, still rational. I'm going to put that over here. How about, let's say, how about a half? Do you think a half is rational or irrational? Maybe you're catching on to a trend. A half is going to go over here. How about like 0.75? Rational, irrational. 0.75, I would say, is pretty close in character to 1/2. That's going to go over here. How about 0.3 repeating? 0.333 just keeps going forever. 0.3 repeating. That seems like a weird one, right? Well, guess what? Still rational. How about something like pi? Pi is going to be our first irrational on the list. How about something like square root of 7? Square root of 7 is going to be another irrational on the list. Okay, so maybe you're seeing some patterns here. What is the difference between the rationals and the irrationals? Well, if a number is rational, that means it can be written as a fraction. There is an exact fractional value for that number. For example, 4. We could make a fraction by putting a 1 under it. Same with negative 4. Same with 0. 1/2 is already obviously a fraction. 3/4 is the same thing as 0.75. And then 0.3 repeating, that's the same thing as 1/3. Anything that has an exact fractional value is a rational number. If there isn't an exact fractional value, if it cannot be written as a fraction, what you see is a non-repeating, non-terminating decimal. So pi, for instance, we know is 3.14, approximately 3.14, and the decimal goes on forever without any repetition. The same thing would happen for something like the square root of 7. Square root of 7, if we put that into the calculator, is 2.654, so the decimal just keeps going forever. So it's about 2.65-ish, right? It's about 2.65, but the decimal continues on without repeating. So this is going to continue on, but because it repeats, there is an exact fractional value for it. Okay? So my point to all this is, well, one, a little refresher on number classification, but the word rational, you really should be equating with the word fraction. Okay? Rational means fraction. So when we are dealing with rational expressions, rational equations, rational functions, we are looking at not just fractions, but fractions of polynomials. Those would be all the things we were factoring in module 1.5. So when we're factoring a difference of squares, we're factoring a polynomial that could have a degree of 2, right? Or we're factoring a quadratic trinomial, that's a polynomial. When you're factoring, quadratics, linear, cubic, all those expressions are polynomial expressions. When you make a fraction of those, then you have a rational expression. So a rational expression will contain a fraction of polynomials. And keep in mind, we're just going to sort of assume that this is true for the expressions that we're working with, and we'll talk more about it when we get to equations, but when we're dealing with the fraction, the denominator cannot equal 0. So we just sort of assume that this doesn't happen, but the denominator of a fraction cannot equal 0. And again, we're going to talk more about that later. All right, so what I have for you are 3 examples of rational expressions. This is a fraction of polynomials, a fraction of polynomials, a fraction of polynomials. Okay? Now, just to be clear, if I had something, let's say the reciprocal of the first example. If I flipped the first one and made it x plus 1 over 2, that one is no longer rational. Not rational, because there isn't a polynomial in the denominator of the fraction. So I'm going to say a fraction of polynomials just to be concise with the wording, but specifically we have to have an x in the denominator for it to be rational. And if you were to graph each of those, what you're going to see for the first, the second, the third will look like the parent rational function that we graphed in our parent function section. And if you were to graph that last one, then pink there, that's not rational, you're going to see a linear function. So you can look graphically to determine, but we have to have specifically x in the denominator of a fraction for it to be a rational expression. Okay? So what we're going to be looking at in this first lesson is just simplifying rational expressions, which means we're just simplifying fractions. So if I said to simplify a fraction to you, what does that mean? Well, hopefully it's meaning to reduce the fraction. And a rational expression can only be reduced if all of the terms in that fraction, all of the terms in that rational expression, top and bottom, have something in common. Specifically, we're looking for like a GCF. Is there something that all of the terms have in common? So looking at this example here, we've got 2 terms. We've got the 10x in the numerator, we've got the 15x squared in the denominator. Is there something that those 2 terms have in common? Again, think in terms of a GCF. Well, the GCF for those 2 terms, if it's anything other than 1, then yeah, we can reduce. So we would say that this first fraction is reducible. Reducible by the 5 and the x that they have in common. Now the next fraction, how many terms do we have? Well, we've got a 4x cubed, a 2x, and a 6x squared. That's 3 terms. Is there something other than 1 that goes into all 3 of those? Is there a GCF other than 1 for all 3 of those terms? Yeah. So we would say that this fraction is reducible by the 2 and the x that they have in common. Okay, now how about this next one? This is a tricky one. I'll see a lot of mistakes on something like this. I'll see a lot of people want to say, oh, we can reduce. Like this becomes a 1 and a 2, and those x's just cancel. But let me ask you the same question I started with on the others. How many terms do we have in this fraction? Well, this particular fraction has 1, 2, 3, 4 terms. Is there something that all 4 of those terms have in common? Well, no, 2 of them have an x, but the other 2 don't. 2 of them have a 4 in common, but the other 2 don't, which means this fraction is not reducible. Not reducible. Okay? Now what do you think about the last one? How many terms do we have in that last fraction? Well, because this is a product, this is all sort of lumped together as one term. And then on the bottom, what do you think? Do you think this fraction is reducible? Well, remember, our GCF doesn't have to be a single term. Our GCF can be a binomial. And if the top and the bottom have that binomial in common, then that would be our GCF. So this is going to be reducible by a binomial factor of x plus 1. Okay? So, hopefully we can identify when we're looking at a rational expression whether or not it can be reduced. Sometimes it can't be reduced up front. Sometimes we have to do a little bit of work before we can reduce. But what are we doing to actually reduce? Okay? If we have recognized that the terms in our fraction are reducible, how do we go about reducing? Just like we would reduce, if I gave you 6/18 and I said to simplify or reduce that fraction, well, you recognize that they have a 6 in common, just like we recognize a 5x here, 2x here, or an x plus 1 here. What we do to then reduce is divide, right? If I recognize this has a 6 in common, top and bottom, then I would divide by 6. So 6 divided by 6 would be 1, and then 18 divided by 6 would give me 3, and there would be my reduced fraction. Okay, same thing here. We're just going to be dividing by GCF, a polynomial. So we're going to reduce by dividing every term by that greatest common factor, GCF, or if you're using Desmos to help you identify, it's GCD. And then remember to use your quotient rule. So for example, if you took, I don't know, 20x to the fourth, and you were dividing it by 2x to the second. Well, we're going to divide the coefficients. The 20 divided by the 2 would make 10, and then we subtract these out. If you have 4 x's, but you divide 2 out, those 2 get subtracted out, so then you'd have x squared left. Okay? So that's technically called a quotient rule. For polynomials, it says to divide coefficients and subtract exponents for like bases. All right? So if we look at number 1, hopefully recognizing those two terms have something in common. These two terms are reducible by a GCF of 3 and an x to the fourth. So we're going to divide each of those terms by 3x to the fourth. So on the top, 18 divided by 3 is going to be 6. And if you had 4 x's but you divide 4 out, no x's left on the top. And then on the bottom, 3 divided by 3 is 1. And we won't have to put the 1 here because we're going to have 3 x's left over to hold the place. Okay, so we divided each of those by 3x to the fourth. And boom, that's our simplified expression. Okay, second one, we've got 1, 2, 3 terms. They all have something in common. What can we divide out of these 3 terms? Well, let's see, the GCF would be a 2, an x, and a y. So on the top of the fraction, we're going to divide here. If we divide by a 2, an x, and a y, we're going to have an x left. If we divide here, negative 4 divided by 2 is going to be negative 2. And then if you subtract out an x and a y, you're going to have 1y left. And then if you divide here, 8 divided by 2 is 4. And then if you get rid of an x and a y, you're going to still have x squared y squared left. And that's that. That would be our simplified fraction. Okay? The next one, let's see. Next one, we've got a binomial in common to the top and the bottom. So even though there aren't parentheses here, I could easily put parentheses there. It doesn't change my problem. And so an x minus 5 is in common to our numerator and denominator. So we can just divide that out. We can just reduce that out. So I'm okay with you just putting the line through to reduce it, but just so you can see how this is the same thing we were doing a second ago. If I took this and divided by an x minus 5 on the top, what's x minus 5 divided by x minus 5? It's a 1. And on the bottom, when you divide here by x minus 5, that piece becomes a 1. All we're going to have left is the 5. So again, if you just put a line through it and said, oh, there's 1 left on top, 5 left on the bottom, I'd totally be okay with that. But just so you see, we're still dividing that out, which makes that binomial go away. So 1/5 is our answer. And I guess that fraction bar is a little ginormous. So let's fix that. All right, so if you feel good about this, then go ahead and give the next one a try. If not, let's see. GCF for these 3 terms is going to be a 7 and an x squared, so all 3 can be divided by 7x squared. So 14 divided by 7 is going to leave us with 2, an x squared left. Negative 7 divided by 7 is going to be a negative 1, and this time I have to put the 1 because both x's are going to go, so we need the 1 to hold the place. And then on the bottom, 7 into 21 is going to be 3 with an x left, and that is our simplified answer. Okay? Not so bad, right? Alright, so far so good. Now let's try to see where this factoring that we looked at in Module 1.5 is going to come in. If we look at example 4, right now we've got 1, 2, 3, 4 terms in this fraction, and those 4 terms have nothing in common. The top 2 terms have a 3 in common, but the bottom don't. The bottom 2 terms have a 5 in common, but the top don't, right? There isn't something that all 4 of the terms have in common, which means this fraction can't be reduced as is. Now that doesn't mean it can't be reduced, it just means it can't be reduced as is. So if you have a fraction that can't be reduced right up front, what you're going to attempt to do is factor it and then see after it's factored if you can reduce. So here, for example, the top of the fraction is factorable. Since both the terms on the top have a 3 in common, I can't reduce it out, but I can factor it out. So I'm going to rewrite the top as 3 times x minus 2. And then the bottom, again, I can't reduce out of 5, but since the bottom 2 terms have a 5 in common, I can factor out that 5, and what I'm left with is another x minus 2. And now, instead of 4 terms in my fraction, I've got 1 term on the top and 1 term on the bottom. And what do those 2 terms have in common? they've got an x minus 2. So now we can reduce out that x minus 2, and then we're good. The leftover 3 on top and 5 on bottom, that's our answer. So 3/5 is our simplified fraction. Okay? So if a rational expression can't be reduced first, then we want to factor wherever that's possible. And remember, factoring could be GCFs, grouping. We did not learn to split the middle, sorry. We did bottoms up. There's like 100 ways to factor trinomials. Bottoms up, squares, cubes, whatever that factoring, all the factoring we talked about in module 1.5, all of those could be applied here. Once it's all factored, then we can try to reduce out any factors that our numerator and denominator have in common. And it could be binomial factors, it could be monomial factors, whatever size, right? Remember, GCF can be any size, okay? So if you want to try this next one, give it a shot. Otherwise, let's see. All 4 terms have nothing in common, so this cannot be reduced as is, but it can be factored, because the 2 terms on the top have a 2 and an x in common. So if we factor that out, it's going to leave us an x minus 8. On the bottom, the 2 terms have in common a 5, so if we factor that out, we're left with an x minus 8. So I couldn't reduce up front, but I could factor. Now that I've factored, I can see the x minus 8s are going to cancel, and what we're left with is 2x over 5 for our simplified fraction. Okay? Not so bad. All right, number 5. 1, 2, 3, 4, 5 terms. Do they have anything in common? They do not. So what we're going to do is we're going to factor. And remember, to factor 4 terms, we use the grouping process. So what could we take out of the first group? Is a 4x squared. And if I divide both of these by 4x squared, we're going to be left with 3x and then plus 1. And then the second group, these are both divisible by 3, so I'm going to take out a 3. That's going to leave me another 3x plus 1. And on the bottom, I technically still have my 3x plus 1. Now at this step, I would say we can reduce. Like, technically you want to keep factoring, that's going to be fine. But we've got one term here, a second term here, and if we wanted to group this, we could call this one binomial on the bottom. Don't those all have a 3x plus 1 in common? Yeah, so at this step, if you recognize you can reduce all 3 of those and see that 4x squared plus 3 is going to be your answer, that would totally be fine. But if not, that's okay. We can also continue to factor. I'll show you what's going to happen. On the top now, if we continue our grouping process, we can factor out the 3x plus 1. That's going to leave us the 4x squared plus 3. And then on the bottom, we still have our 3x plus 1. And either way you look at it now, we have a 3x plus 1 in common to the top and bottom. So once that's reduced out, we are done. Our answer is the 4x squared plus 3 that is left over. Not so bad. Okay? Cruising right along. Next one is a little different because we're going to be able to do both factoring and reducing, or actually reducing and then factoring. If you'll notice, 3x, 6, 3x squared, 15x, and 18, they all have something in common. What do they all have in common? Well, they're all divisible by 3. So actually I can start this problem by reducing. So I'm going to reduce by dividing each of these terms by 3. That's going to leave me an x plus 2 on the top, and then an x squared plus 5x plus 6 on the bottom. And now it's reduced. Doesn't mean that we're done because the bottom is still factorable. So we have this x plus 2 on the top. On the bottom, what are the factors of 6 that make 5? Factors of positive 6 that make positive 5 are going to be 2 and 3. Dividing those by 1, not going to change. So the bottom is going to factor into an x plus 2 and an x plus 3. And now I can see the top and bottom of my fraction have a common binomial, x plus 2, so that's going to reduce out. Now be really careful here. I will see a lot of people say that x plus 3 is the answer. No, x plus 3 is part of the answer, but notice where it is. It's on the bottom of the fraction, and it's got to stay on the bottom of the fraction. Technically, what's left on the top? Well, again, if I put parentheses around this and put a 1 here, did I change anything? No. So technically, there's still a 1 left on the top of that fraction. So our answer is 1 over x plus 3. Okay? Alright, so if you're feeling good about this and you want to try it out, go ahead and give this one a shot. If not, on the top, the 5 terms in this fraction don't have anything in common. But on the top, we can factor. On the top, there's a GCF of 5. So if we factor that out, we're left with x minus 3. On the bottom, we're going to go through our bottoms up process. So 2 times negative 6, or 2 times negative 3 is negative 6. Factors that make negative 5 are going to be negative 6 and 1. And if we divide those both by 2, we're going to end up with 1x minus 3 for a factor. 1x minus 3 for a factor, which makes sense. We got one of those in the top. And then 2x plus 1 for the other factor. Okay, and now I can see a binomial in common. Both the top and the bottom have an x minus 3 in common, so that's going to reduce out. And what's left over is a 5 in the numerator and a 2x plus 1 in the denominator. And that is our final reduced answer. Okay? It's not so bad. Hopefully you're feeling that. Alright, we got one left to try again. If you feel good about this and you want to give it a shot, knock yourself out. So, I see a lot of mistakes happen on a problem like this. I will see a lot of people that want to just reduce here and reduce here. Not able to reduce pieces of the fractions separately like that. You have to think about how many terms you have in your fraction and if all the terms have something in common. So these two terms have x's, but these don't. These two terms have a 9 in common, but these don't. So this fraction is not reducible as is. Alright, so be really careful. Not reducible, but it will be after we factor. So on the top of the fraction, hopefully you're seeing this is a difference of cubes. This is x cubed minus 3 cubed. And on the bottom, this is a difference of squares. This is x squared minus 3 squared. So on the top, we have a formula for the difference of squares. Remember, it's the binomial with the bases of those cubes, and then the trinomial where we multiply or square the first term. I think I showed you the signs first, right? When we factor cubes, it's a binomial times a trinomial where the signs are the same, and then the opposite, and then always positive. The bases of the cubes go into the binomial, and then we square the first term, multiply the two terms, and then square the second term. So we're going to put a 9 here. And then on the bottom, we're going to end up with conjugates, an x plus 3 and an x minus 3. An x plus 3 and an x minus 3. And now that it's factored, I can see the top and bottom both have an x minus 3, so we can reduce those out. So we are left with this trinomial on the top, x squared plus 3x plus 9, and binomial on the bottom, x plus 3. And there might be some temptation to try to go further here. But we have got 5 terms. They don't all have a 3, they don't all have an x, so this cannot be reduced. And you could try to factor on the top, but there won't be any factors of 9 that make 3. And in fact, your trinomial that results from factoring a sum or difference of cubes will never be factorable. So since the top isn't factorable, the bottom isn't factorable, and we have nothing in common, that means this is our final answer. Alright, and there it is. So you've got some practice problems to work through. Get going on those, and if you find yourself struggling and you need any help, just reach out. I am here for you. Alright, guys.